Welcome back to the Explainer, everyone. Today, we are talking directly to all the working developers out there. So if you've been tinkering with large language models lately, you already know they arrive with some seriously impressive capabilities right out of the box, right? But as developers, we usually hit a ceiling pretty quickly. We suddenly realize that we need these models to do way more than just write boilerplate code or summarize public internet knowledge. We actually need them to understand our specific internal systems. And that is exactly what we are tackling today. Our goal is to move way beyond basic AI APIs and really master designing a Retrieval-Augmented Generation system, or RAG for short. This is the exact architectural pattern you absolutely need to securely connect LLMs to your own proprietary data. So grab your notes, get comfortable, because we're going to dive deep into this source material together and sketch out a complete, rock-solid mental model for getting a RAG system production-ready.
Here is our roadmap for today's explainer. First, we'll tackle the blank slate problem. Then, we'll officially enter the world of Retrieval-Augmented Generation. From there, we'll break down the four-stage RAG pipeline, dig into context engineering and chunking, and wrap up with some really cool advanced RAG architectures.
Starting off with Section 1, the blank slate problem. To really understand why RAG is such a game changer, we first need to get perfectly clear on the core problem we're trying to solve. Large language models are, without a doubt, incredibly smart, but they are essentially total blank slates when it comes to your internal, private data. Think about it like this. If a user asks an AI, "Who are the Beatles?" the model can give you a brilliant, historically accurate answer instantly. Why? Because it literally ingested all of Wikipedia during its training phase. But if your user asks your brand new AI support agent, "Hey, I'm having password issues, can you help me?" the LLM is going to be completely stuck. It might be able to ace a pop history test from the 1960s, but it has zero awareness of your internal wikis, your specific IT protocols, or your past support tickets. It simply lacks the private context to be of any real use.
Moving right along to Section 2, enter Retrieval-Augmented Generation.
So now that we clearly see that massive limitation, we obviously need a way to bridge this gap. We have to connect this powerful generalized model to our highly specific private data silos. And Retrieval-Augmented Generation is exactly that dynamic bridge. It's an architectural pattern, and its entire mission in life is delivering exactly the right pieces of your private data to the LLM at the exact moment that data is requested. By doing this, RAG effectively turns an LLM from a generalized know-it-all into a specialized, highly focused expert on your specific company. You're basically taking the incredible reasoning engine of the AI and feeding it your own custom facts right before it answers.
The source material gives us a really crucial shift in mindset here. It points out that RAG is not just about searching for data, it's really about shaping the context. As developers, it's so easy to just think of this as running a standard database query and dumping the text results into a prompt. But true production-ready RAG requires us to think deeply about context engineering. You are selectively, carefully curating exactly what the model sees. And why does this matter? Well, good context engineering directly lowers your API costs by massively reducing token usage. It heavily reduces those dreaded AI hallucinations, and it measurably, undeniably improves the quality of the answers your users actually get.
All right, Section 3, the four-stage RAG pipeline. We know the why, so let's get into the how. How does this actually work under the hood? Well, we can break down the core mechanism of RAG into a very logical linear sequence that you can quite literally start building today. Every RAG system out there, no matter how wild or complex it gets, fundamentally operates as a filter through four distinct stages. We have ingestion, retrieval, augmentation, and finally, generation. Truly understanding this exact sequence is the absolute key to building your own solution. You can sort of picture this whole pipeline as a giant funnel. It starts with all of your messy, raw corporate data at the top, and it ends with a single, highly accurate, perfectly formatted AI response at the bottom.
When we look at the complete workflow from end to end, we can really see how this becomes such an elegant, closed-loop system. We always start by taking our raw documents, chunking them down into much smaller pieces, and embedding them into a specialized vector database. That's the setup. Then the cycle shifts over to the user. When a user actually makes a query, we mathematically embed their question so we can find a semantic match in our database. We retrieve those relevant document chunks, combine them tightly with the user's question into what we call an augmented prompt, and finally, we pass that complete context-rich package over to the LLM to generate the final answer. It's a beautiful, continuous loop.
Let's actually zoom in on the very start of the pipeline, the ingestion phase. This is where all the heavy lifting of data prep happens. Look, we obviously can't just throw massive 1,000-page software manuals at an LLM. It would break the context window and cost a fortune. Instead, we use document-based chunking to break our data down into manageable, sentence or paragraph-sized pieces. Once we have those chunks, we use an embedding model. Our source material specifically highlights a high-performance model called MX by embed large. We use this to convert those text chunks into mathematical vector embeddings. These vectors are amazing because they capture the actual underlying semantic meaning of the text. This allows us to load them into a vector database, like Chroma, so they just sit there, perfectly organized, ready for lightning-fast retrieval later on.
Now moving to the second half of the pipeline, this is where all that prep work pays off for the final user experience. When your user asks a question, the retrieval stage kicks in. It performs a similarity search in our vector database to pull back the top K most relevant chunks of data, basically the chunks that mathematically match the meaning of the user's question. Next up is augmentation. We take those retrieved chunks and we merge them with the user's original query. But we don't just mash them together. We use structured prompt templates that include very strict system instructions for the AI. Finally, in the generation stage, we send this richly populated, highly controlled prompt over to the LLM. And because the LLM now has exactly the context it needs, securely wrapped in your instructions, it can stream back a highly accurate, context-aware answer. Zero hallucinations.
Next up, Section 4, Context Engineering and Chunking.
Okay, so those 4 stages we just covered, they will absolutely allow you to build a fantastic prototype. But out in the industry, they actually refer to this basic, out-of-the-box implementation as naive RAG. Now, naive RAG works wonderfully for small, perfectly curated knowledge bases, or for a weekend hackathon where just good enough answers are acceptable. But if you rely exclusively on basic chunking in a real production environment, I guarantee you will inevitably hit a wall. When you start dealing with massive, noisy databases or really complex user queries that just don't map cleanly to your stored chunks, things start to break down. We have to get much smarter with our data if we want to scale.
To really boost accuracy for production, developers employ some brilliant advanced refinements. For instance, you can use metadata-aware hybrid search. This lets you filter results by things like date, or author, or department before the AI even gets a chance to look at them. But another absolutely massive upgrade is re-ranking your retrieved results. This is such a cool developer trick. You see, LLMs actually suffer from a known quirk called the lost in the middle effect. If you stuff a massive prompt full of context, the model literally forgets the information that's buried in the middle of the text. It's wild but true. Re-ranking is the clever trick we use to ensure your most vital, highest-scoring data chunks sit exactly at the very beginning or the very end of the prompt, which is right where the AI happens to be paying the most attention.
This brings us to a really common chunking dilemma and the solution to it, the parent-child strategy. Think about this. When users ask highly detailed questions, you need really small micro-level chunks to find an accurate semantic match in your vector database. But if you only feed the LLM that single, isolated sentence you found, it completely loses the broader context of the document. It won't know what that sentence actually means in the grand scheme of things. With parent-child or 2-level retrieval, you store the ID of the larger parent document right in the metadata of the smaller child chunk. So you use the highly specific microchunk to find the perfect search match, but then you retrieve and feed the LLM the entire macro-level parent document. It's just a brilliant way to maintain surgical search accuracy without sacrificing the surrounding context the AI needs to actually write a good, coherent response.
And finally, Section 5, Advanced RAG Architectures.
As your application scales up, you have to actively match your architecture to your user demand. You can think of this as a sort of developer's cheat sheet pulled straight from our source material for matching specific RAG architectures to specific production needs. For example, if you have a massive, really noisy knowledge base, you are definitely going to want hybrid RAG. This combines traditional keyword search with vector search, making sure you catch exact terminology right alongside the semantic meaning. On the other hand, if your app handles high-traffic, repetitive questions like an FAQ bot and it needs ultra-low latency, you'd use Cache-Augmented Generation, or CAG. This reads directly from a lightning-fast in-memory cache to just bypass that heavy search step entirely for common questions. Now, what if you need fast-changing data, like live stock prices or live inventory? You use API-Augmented RAG, where the LLM issues a real-time tool call to an external service. And finally, for scenarios demanding high factual accuracy with perfectly traceable reasoning, think medical, legal, or compliance fields, you would use Knowledge Graph RAG. This stores facts as directly connected logical nodes rather than just text chunks.
The main takeaway I want you to have here is to just not get overwhelmed by all this terminology. Whether you are using cached, agentic, API-driven, or graph-based variants, you are still, fundamentally, just applying clever modifications to that original 4-stage pipeline we learned about earlier. You're simply changing the way you ingest, retrieve, augment, or generate to perfectly fit your unique application's requirements. At the end of the day, it all traces right back to those basic fundamental building blocks.
By connecting these models to your proprietary wikis, your databases, and your internal support tickets, you have essentially unlocked an incredible amount of automation potential for your software. You've completely transformed a blank slate AI into a specialized, incredibly knowledgeable expert tailored exactly to your business. Which leaves us with one incredibly exciting question to end on as you head back to your code base today. Now that your LLM can securely read your private data, what are you going to teach it first?